right, so today, whole new topic, whole new subject, whole new approach. Going out of the time domain into the frequency domain to give ourselves a different way to look at things. We're not changing our signals, we're just changing the way we look at them. We're not changing our systems, we're just changing the way we look at them. We're taking ourselves from a signal standpoint from looking at things like we do on an oscilloscope, how do functions change versus time. Now with discrete time signals, we're talking about sample values of functions as they change versus time. And instead of looking at them in this perspective, we're looking at them like we would see on the spectrum analyzer. How much frequency content is there at various frequencies? So it's all the same information that's carried in this depiction of the time domain signal is also present in this depiction of a frequency domain signal. Well, at least it is as long as if I give you magnitude and phase information along there, not just magnitude. It's just another perspective, another way of looking at the same information in a form that's maybe more convenient for some of the things that I want to do with that signal or that system. And so before we go deep into it, let's kind of see why are we going here? What's the big deal? Why are we going to spend so much time in the frequency domain when the real world is time domain? And well, if we relate it to if you're going to actually design something, it turns out the language that we use in design, in the language that the things we care about when we design signal processing systems have more of a frequency flavor than they have a time domain kind of flavor. If you think about you're trying to design a system, you're probably trying to manipulate the frequency content of your signals. There's certain ranges of signals you're trying to either let through or enhance, even boost up. There's other ranges of signals you're probably trying to get rid of. And so the jobs we need to do, the approaches we need to take have more of a frequency kind of perspective to them. And one of the big problems we have with signal processing and systems design is noise. And noise comes in many forms, but some kinds of noise are very broadband, have a lot of frequencies in them, but some of the more annoying kind exist only at particular frequency or particular harmonics. How many guitar players in the audience? Electric guitar players. Plug in your amplifier and what do you hear when you turn up the volume a little bit? 60 hertz noise. Ubiquitous. Depending on how good the grounding system is in your amplifier and your whatever you're plugging it into, it can be really annoying. So there are cases where there's very particular frequencies that we want to get rid of, and maybe we will design filters to attenuate those particular frequencies. So noise tend to be something that we need to understand. What's its spectral content? What's its frequency content? So we know how to deal with it. And when we're designing filters or systems, even the specs that we write up tend to have kind of frequency sort of things, senses to them. Like we design filters with certain cutoff frequencies, or we want a certain amount of so many dB of attenuation at some stop band edge frequency. So this is the world that we usually design or specify our systems in. Not, I want a filter with AK equals 2 and BK number, or B2 equals 3. That's the design, that's what is the result of our design, not the intent of our design. Right? The intention is to achieve some frequency characteristic, and then we as designers have to figure out, well, how do I manipulate those difference equation coefficients so that I end up with a filter that has those frequency characteristics. So we think about, and we describe our problems in the frequency domain, and then have to solve them with things that will execute in the time domain. So we need both perspectives, but the more natural one for talking about design analysis is going to be the frequency domain. All right. If we talk about system responses, well, we've been spending, we spent several weeks learning how to describe how to solve for the response of a system in a time domain. And we came up with 3 approaches: recursion tables, not so hard; solving difference equations, painful; and convolution that are okay if you do them by tables, but if you want an analytical solution, they're really a nightmare. We're going to take those problems and move them to the frequency domain, and the reason we're going to move them is that they're easier to solve there. Particularly this nasty summation thing called convolution turned into simple multiplication in the frequency domain or in the Z domain. And also, if I have a frequency-based picture of the response of a system, then I have basically a lookup table for figuring out how is the system going to respond to any sinusoidal signal that I put in. If I put in frequency 5, I can look up in my frequency response, frequency 5, and see what the system's going to do. We have this, just like we had in continuous time systems, if you have a frequency response kind of description of your system, and you put in a particular cosine of a particular frequency with some magnitude phase, put that into that system, we know without doing convolution, without doing transforms, without doing any of that stuff, we can tell you exactly what comes out. All the system is allowed to do, if it's a linear time invariant system, all it can do to a cosine is send that cosine back out. You can't change the basic shape, you can't change the frequency. The only thing it can do is scale the magnitude and add or subtract some phase to it. And how much it scales the magnitude and adds and subtracts phase is exactly the information that's captured in the frequency response. And so the frequency-based description has all the information that I need to solve any system analysis problem, but most particularly, if you give me a sinusoidal input, I can directly, without any fancy computation, tell you what comes out. Yeah.
I'm kind of confused on the translation between the two different ways of looking at it, because like when you have a time domain graph of, say, a transfer function, and it's giving you like the response over time.
Right.
When you go into the frequency domain, it just says at this frequency, this specific number is going to be the amplitude of the response. But it doesn't really give you like an over time view of like what's playing out.
So the time domain response tells you kind of how the response changes versus time. But if you have a single number in a frequency response, that doesn't really tell you anything about any temporal change going on.
Yeah, like you can't see that. It's hard to tell what it means.
Yes, that's very true, because so this that I described up here, we would consider a forced response, a steady state response. I'm not going to see any transient here with this kind of signal. This is a cosine that somebody turned on just after the Big Bang. They turned on the function generator, and it's been running for a while, and it's going to keep running forever. And that's the kind of cosine we're assuming. No transient. So this gives me a shortcut. So it's a really good point. It's a shortcut answer to the steady state response, not a complete response. So okay, so it has that limitation. If I want the complete response, including the transient, well, I can still solve this problem in the transform domain. I just can't take this particular shortcut. And I've got to implement convolution of sorts translated to the frequency domain, which we can do, which we are going to do, to get the complete answer. So thank you for correcting that. Okay. But at least what I want to do is convince you that this new perspective, this new way of looking at it is actually useful, actually going to be helpful, right? So, what is it that we need? Well, we need some way to get a time samples and rearrange in a way that we now have frequency information. So, and different from what you've done before in 228, we need a transform, a mathematical transformation that works on discrete time signal, that works on samples, not a continuous signal. Now, go back to our buddy Mr. Fourier. He says, I have this beautiful transform. Why don't I not make you a discrete time version of my beautiful transform? And we say, okay, well, fine, that sounds good. So he's got an x sub f thing, and he's got an integral, and well, we wanna, in terms of our new digital frequency, that's really what we want. So, Mr. Fourier, how do you want to do that one? Well, we know the continuous time Fourier transform. You all are good about this from 228, right? It was just another way of taking a time signal and looking at it kind of in a orthogonal axes, looking at how much frequency content it has at different frequencies. But all the same information is there, whether I look at it from a frequency standpoint or a time standpoint. And we use these integral transformations to get me from one domain to the other or back the other way if we need to. So we could take a signal out of the time domain, put it in the frequency domain, and send it back at will, using what were very, very similar transformations. In fact, so similar, the only thing I changed was the minus sign and the variable integration. That's the continuous time version. We want to adapt that to our discrete time version. Well, what is this thing? Well, it's the thing we're going to come up with is very much like that continuous time Fourier transform. It's still going to give us a frequency domain picture. It's going to answer questions like how much signal is there at a given now digital frequency in our sampled signal, not a continuous signal. Or for systems, it's going to tell us what's the system going to do, what's its response to signals of different frequency, particular cosines. So all that same kind of information that we had in continuous time Fourier transforms is going to be available to us in the discrete time version. And unfortunately, just like continuous time Fourier transform, it's going to be a complex valued function, which means we're going to have to depict it with, well, either magnitude and phase or real part and imaginary part. There's two pieces here we always have to keep track of. For us, it's going to be more helpful, more functional, more useful to look at magnitudes and phase, because those, to me, will have more meaning that I can connect to the physical world and physical phenomena as opposed to real and imaginary parts. So that'll be the typical way we'll look at those. Okay, that way they're similar. Different, however, in that, well, we saw this with sampling theory when we talked about, we tried to find a spectrum, a frequency, look at a sampled signal, and lo and behold, we saw that the sampled system seemed to have a spectrum that repeated and repeated and repeated with a periodicity, a period of f equals 1. So the same thing that was going on at f equals 0 happened at f equals 1, and happened again at f equals 2, and 3, and 4, and so on. So this transform we come up with has to end up with a periodic answer. It has to produce this kind of periodic spectrum, because we saw from sampling that's what we're supposed to get. And things like aliasing that kind of periodicity describes or says should be happening, we can actually find as a true physical phenomenon. So it needs to be there. It needs to show up in this new transform. Okay. And the big difference, this is a spectrum now that acts not on continuous signals, but on sampled data signals, or sampled unit sample responses. Okay. So how are we going to get there? Well, we actually almost derived it back in sampling theory. And we can use some of the same models and arguments that we did there to come up with this new transform. Remember that model we had for sampling? That you could try to explain the phenomena if you said we're taking a continuous time signal and multiplying it by an impulse train to make a discrete time, well, kind of quasi-discrete time signal, a signal that was sort of our continuous time version of a discrete signal. Right? So take a continuous x of t, multiply it by an impulse train, where those impulses were happening at every sampling instant. So at 0, 1 times t sub s, 2 times t sub s, 3 times t sub s. And when I multiply those two together to see what comes out, well, we've got a bunch of weighted impulses using the multiplication property of impulses. So an impulse would be weighted by the value of x of t at the time of the impulse fired, and I would get this collection of weighted impulses. So I could describe this continuous time version of my discrete time signal, those sample values, using the summation, sum of these bunch of shifted deltas, shifted by integer multiples of the sampling interval, multiplied by the value of the original function at those same instances. Well, we'll take that model again, try to take its continuous Fourier transform, because it's a continuous signal, and because we know how to do those, and see what we come up with, see if we can kind of manipulate it into being the kind of transform we want for a discrete time signal. Everybody okay with how we're going to do that? Okay. A little review first. If I have x of t as a time function, we call it continuous time Fourier transform x of f, little f. We know that if x of t produces x of f and y of t's Fourier transform is y of f, if I put in a signal that looks like the sum of x of t and y of t, run that combination through the Fourier transform, their transform should also add. That was additivity that came out of the fact that Fourier transforms are linear operations. Likewise, I could even scale x and y by the same or different scale factors, and their transforms would also scale by the same. That's linearity. That's true for systems, but it's also for linear time-varying systems. It's also true for linear operations like the Fourier transform. So this is true. What is the Fourier transform? Continuous time Fourier transform of a continuous time impulse, delta of t. Anybody remember? Continuous time Fourier transform of a delta. I hear some mumbles. You're just got to be louder because you're right. One. Okay. So if the Fourier transform of delta of t is 1, the Fourier transform of a shifted delta, shifted by a, delayed by a, well, we can use the shift property of Fourier transforms. It says if you shift something, you multiply its Fourier transform, 1, by this quantity, e to the minus j 2 pi f times the amount you relate out. So this is both the transform of an impulse and using the time shift property. Why did I do that? Well, here's our description of a discrete time signal. It's a bunch of weighted, shifted impulses, a whole sum of them. Well, with these rules, I can exactly predict the continuous time Fourier transform of the summation. It's also going to be a summation. It's also going to be scaled. But I'm going to take the Fourier transform of a delta function of a shifted delta, which is just e to the minus j 2 pi f times the amount I'm shifting it in t sub s. So with these rules, I know what the continuous time Fourier transform is of my continuous time model of a discrete time signal. That's a mouthful. Okay, so if I model my x sub n signal as this, its continuous time Fourier transform is this. That's what we just said in the other slide. All right, that's close actually to what I want. Except I'm going to change my variables because it's in terms of analog frequency and t sub s. Don't like that. I want something in terms of my new digital frequency, capital F. We know that digital frequency is just a normalized version of the analog frequency, so it's f over f sample. And f sample is the reciprocal of the sampling interval t sub s. So everywhere I have a f t sub s in my summation here, I can replace it with capital F. And I can also recognize that x sub n, the continuous function at n t sub s, are exactly the same as the sample values I'm going to pull out from my x sub n sequence. So we can recast this continuous transform into the form we want for our new transform. Now a function of digital frequency capital F. It's just a sum over all n. X sub n, not x sub n t sub s, because same values though. And we replaced the f t sub s by capital F. So we have e to the minus j 2 pi n capital F. And that is the discrete time Fourier transform. That's the thing we're looking for. So by definition then, if x sub n is a time sequence of values, of sample values, using index n, which are integer indices, its discrete time Fourier transform of that time sequence is exactly given by that equation. X of f is the sum over all n from n equals minus infinity to plus infinity, right? Time sequence x of n times the exponential e to the minus j 2 pi n, same index n, capital F my new digital frequency. And please write that in your notes. It is missing from your notes. And you need practice writing it because you're going to need to know what that equation is. Now, that's it. While you're writing, I will say that is not the discrete Fourier transform. That is not the thing we use when we do signal processing by FFTs and DFTs in computers. This is the honest-to-goodness, absolutely mathematically correct frequency spectrum of a discrete time signal. The thing we call the DFT, well, so what do I mean by that? So this is it's a periodically repeating spectrum, right? Come on, give me a marker that works. It's a periodically repeating spectrum. Keeps going, keeps repeating, keeps repeating, keeps repeating with a period of 1. And it's a continuous spectrum, meaning it's defined at all values of capital F. It's not a discrete spectrum with sample values. It has values everywhere at all frequencies. Now, that makes it not very useful for doing computation with computers. This is not the thing you want to do to use digital signal processing, but it's the correct transform for a discrete time signal. That thing so this is the DTFT. The thing we call the DFT, the discrete Fourier transform that we'll talk about at the end of the course, that's the sampled version of that. That's one that works really well for computers because I've just got sample values and I can add and multiply and do all the things I need to do with those very simply. But that's not what this one is. And they are related, very related on a good day, not so related if you do things wrong. So there's some special care we have to take, and we're going to hold off that stuff till the end. Today we're distinguishing ourselves that we're working with the discrete time Fourier transform, DTFT, defined by this summation. Okay? All right. Before we use a transform with a nasty equation like that, well, first off, we notice I like this. I like this better than continuous Fourier transforms. It's a sum, not an integral. Much better. Much better. I just got to add stuff up. That always feels better than integrating. But I can't use it if I don't know when I can use it and when I can't. And I have a summation here. I'm adding stuff up. So there's a potential problem here. I can't use this on every single function, every single signal, because this summation has the chance to go off to infinity. That sum may not converge. And if that sum doesn't converge, then I can't compute a valid discrete time Fourier transform. So first we've got to ask, when does this exist? When does this function converge? And well, that'll be our simple starting point for defining when can we use a discrete time Fourier transform. Well, obviously, we can use it when the summation converges. Okay, that's like saying Tuesday when it's Tuesday. But let's take a look at that. So we've got a sum of two different things, x of n and this exponential weird thing. Aren't you getting tired of the minus j stuff? Sorry, they're going to be hanging around for a while. But let's look at that piece all by itself. I want that summation to converge. Meaning I don't want to blow it up. So I probably want it to decay somehow. And is this e to the minus j 2 pi nf, is that as a function going to help me converge? Is that like a decreasing function that's going to help push x of n down? Because remember, Laplace transforms, we added an exponential in there to try to force things to converge, and then we had this cool region of convergence thing, and that made Laplace more powerful than Fourier. And so is this guy going to help? Is e to the minus j 2 pi n f going to help me converge? I see some yeses. I see some more yeses. I see lots of strong yeses. I see a lot of heads unwilling to do anything. And the answer is no, it's useless. How do I know it's useless? How big is that? E to the minus j 2 pi n f, where n is an integer. And f is not, f is a continuous valued function. How big is that? Is it less than 1? If it was less than 1, that would be great. Then it would help me converge. Help me out here. E to the minus j, I have no idea what that is. I can't even conceive of that.
1 over e to the j 2 pi n f?
What, say what?
1 over e to the j 2 pi n f?
It's 1 over e to the j 2 pi n f. Yep, it is. Does that help?
Cosine 2 pi.
Oh, who, what?
Plus I sine 2 pi n f.
Monsieur Euler, friend of Dr. Fourier. This is cosine 2 pi n f. What is it?
Plus I sine 2 pi.
Minus sine 2 pi n f. Okay, so, oh, j, there's a j in there. So Euler identity says that's the same as cosine 2 pi n f minus j sine 2 pi n f. And how big is this? What's the magnitude of this complex value? How did you know that? It's the square root of the sum of the squares of the real part. There's the real part. Here's the imaginary part. So I'll take the real part squared, 2 pi n f, add it to the imaginary part squared, 2 pi n f, take the square root, and cosine squared something plus sine squared something is always 1. So if you've never done that before in 228 or in this class, you now know e to the minus j anything has a magnitude of 1. It doesn't matter what f is, doesn't matter what n is, e to the j anything has a magnitude of 1. It could be complex. It has complex values. The real part and imaginary parts are changed in size, but together they will always give you a magnitude of 1. So that is not helping at all. It's multiplying, its magnitude is multiplying x of n by 1. So no help. If that's no help, then if I want the sum to converge, ergo to it, x of n itself better converge. So we say the discrete-time Fourier transform exists if x of n, the thing I want to transform, is absolutely summable. Just like we used to say for h of n being absolutely summable for a stable system. Okay? So that's the requirement for finding a valid discrete-time Fourier transform. I can only do it for signals that are themselves absolutely summable. Means I can add up all their sample values from n equals minus infinity plus infinity and get a finite value. All right. Now, just like in continuous time, that's the hard and fast rule. There's always exceptions. So, for example, a unit step is a function that, let's draw one, unit step, right? 0, 0, 0, 0, and at n equals 0, it goes to 1 and stays at 1, 1, 1, 1, 1. If I try to add up all these values for n equals minus infinity plus infinity, I get infinity. So a unit step is not absolutely summable. Therefore, it should not have a discrete-time Fourier transform, but it does. So the rule is, if you do have an absolutely summable signal, its discrete-time Fourier transform definitely exists. It's going to have one. If it's not absolutely summable, it might exist. You might have a valid discrete time Fourier transform. And what separates the yeses from the nos is your function can't grow exponentially or faster. So if alpha is raised to the n power or 8 times n power, as long as alpha's, this is wrong in your notes, change it, less than 1. So if alpha's fractional, and I raise a fraction to the n power, that's a converging function. If, and it can, if alpha is, if you have a minus sign here, then your alpha better be greater than 0. If that happens, you're going to end up with some impulses somewhere in the discrete time Fourier transform, some unit sample functions or impulses and frequency, actually. Some good old continuous time impulses, actually. If you have something that grows exponentially or faster, then sorry, it doesn't exist. Okay? So, let's look at some of the properties of this discrete time Fourier transform. Remember when we said it's periodic with a period of 1? Well, our exploration of sampling theory showed us that. It told us that's the right answer. Let's make sure that this thing we derive has that kind of behavior. And notice we're often using a subscript p for our discrete time Fourier transform to remind us that this should be a periodic function. If it is, if this Fourier transform is periodic with a period of 1, this has to be true. If I plug in a frequency f plus 1, I should get the same answer as just frequency f, if it's truly periodic. Or I can put in f plus 2 or f plus 3 if it's periodic with a period of 1. Well, that's easy to do. We can take the definition of a discrete time Fourier transform, the summation of x of n e to the minus j 2 pi n f, and replace f with f plus 1. And then recognize that the sum of exponents is the same as multiplying the base function with the individual exponents. So we have e to the minus j 2 pi f, multiplied by e to the minus j 2 pi n1. And then we ask ourselves, what's that guy? What's that e to the j 2 pi n? E to the minus j 2 pi n times 1, where n is an integer. We'll do our Euler identity again. That's a cosine 2 pi n minus j sine 2 pi n. Sorry, I got a board there. Where n is an integer. Okay, where are we? For n equals 0, what angle am I at? N equals 0, I've got cosine 0 and sine of 0. I'm pointing out this way, angle 0. N equals 1, cosine of 2 pi and sine of 2 pi. And if n equals 2, cosine of 2 pi, or 4 pi, and 6 pi, and 8 pi. I'm always pointing over here, which has a cosine of 1 and a sine of 0. So this is a fancy way to write 1, which does nothing. And so I'm left with the formula that I got by plugging in f plus 1 was the same as the formula without the f plus 1, so they are equivalent. It is a periodic function. So that's good. We got a result that has the correct mathematical behavior. Unfortunately, again, x sub f now is going to be complex, which means we'll probably talk about its magnitude and phase, which we can write magnitude and phase notation, or magnitude in the j phase. It also can be broken up into real and imaginary parts, but again, for our purposes, the more useful way to look at it is going to be magnitude and phase. So that would be the typical way to do it. And they're related, as we did by example here. If we want the magnitude, we take this over the sum of the squares of the real part, squared without the j, imaginary part squared. So make sure you've got squares in your notes and no j in your notes. And obviously the angle is the inverse tangent of the imaginary part of the real part. So if we have this kind, we can get back to here. Okay. Now, some interesting consequences. Some of the same symmetry properties that the continuous time Fourier transform had, the discrete time transform also has. Namely, if your time sequence that you're transforming has all real values, no j's in any of the timing function sample values, well, that's most signals we're going to, that's pretty much all signals we're going to get from the real world, then your discrete time Fourier transform is again going to have even symmetry around f equals 0, just like the continuous time transform did. However, because it's periodic, it's also going to be even symmetric around f equals 1, f equals 2, f equals 3, f equals minus 1, minus 2, minus 3. And if it's going to be even symmetric around those, it also has to be even symmetric around the Nyquist rate, 0.5 and minus 0.5 and 1.5 and 2.5. So even symmetry around even more points than the continuous time version. That's if you have a real values, real sample values in your time function and you take its transform. On the phase side, well, continuous time transform has odd symmetry in the phase around f equals 0, and we have that again here as well. Here, though, we also have that same symmetry around f equals 1, f equals 2, all the integer multiples of the sampling rate, and the Nyquist frequencies. So, again, that's a consequence of having real valued signals in the time domain, real valued sample values. All right? Okay. Questions on that so far? So it's very, 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 very similar to the continuous time Fourier transform. It's computed by a summation, not an integral. The existence properties are similar. It's got to be absolutely summable, not absolutely integrable. It has exceptions, just like the continuous time one does. It's a frequency domain look at our signals or signal content. It's based on our digital frequency, though, now, not analog frequency, so it's a normalized frequency variable. And because of that sampled nature in the time domain, we have these periodically repeating spectra with the discrete time Fourier transform. Okay, if that's all okay, then in the last 10 minutes, let's compute a couple. And as we did with continuous time Fourier transforms, we will use the defining definition to compute the discrete time Fourier transform of some very simple functions and then never do it again. Because from now on, we want to do transforms by lookup tables. We want to be able to look, not go into the summation, not scratch our heads about it, but prove that we can, feel good about ourselves, and then get on with life and do it the practical way, which is just look it up. So let's do a couple of easy ones. First, impulse. Wow, look at this. In the continuous time case, the continuous time Fourier transform of an impulse, let's put a CT in front of that, of a continuous time impulse was a 1. Let's see if we get anything like that in the discrete time domain. So that x of n is delta spin, I have a single sample, one sample with a 1 at n equals 0. Oh, come on, markers. All right. I have one sample with a 1 at it at n equals 0 and 0 everywhere else. That's as easy a signal as I could possibly have. What's the Fourier transform of that? The discrete time Fourier transform of that. Okay, got to plug it into the formula then. So we replace x of n in the Fourier transform formula with delta sub n. And then think about what we're going to do with what we have up there. What's the only place that I'm going to have anything other than 0 with that delta sub n? N equals 0. So that whole summation doesn't matter. Everything except n equals 0 goes away because x of n or delta sub n will be 0. So I'm left with just one term out of the whole summation, the n equals 0 term. And so at that n equals 0, delta sub n is 1, and the rest of the thing is e to the minus j 2 pi 0 times f, which is just e to the j times 0, e to the minus j 0 if you like, which is just 1. So just like the continuous time version, the discrete time Fourier transform of the discrete time version of an impulse is the same as it was in the continuous time version, was 1. Now there's a lot of surprising stuff in that statement. But at 4:53 in the afternoon doesn't seem terribly surprising, I'm sure, because I just don't want to think about what this could possibly mean, because then the class is going to run long. I want to get out of here. Anyway, first observation, I kept saying that this Fourier transform is complex. That is not complex. There's no J there. I got a real valued answer. Right? No magnitude phase, very simple. Why did that happen? Well, what did we say about real time signals? What did they produce? What kind of spectra did they produce? Just said about 8 minutes ago. Real value function gave me a Fourier transform. Magnitude. Even symmetric. Well, duality comes into play again with Fourier transforms, just like they do with continuous time functions. If I have an even symmetric real valued time function, I get a real valued Fourier transform. And this is even symmetric. On either side of 0, it's all zeros. It's an even symmetric function. And so we get a real valued discrete time Fourier transform. Aha. Other interesting observation, this is the coolest signal I have ever seen. Plot that versus frequency. X of f versus frequency. Is it periodic? Strangely enough, it is. I guess you call straight lines periodic. Infinite period or 0, I don't know what you call that. Anyway, it's periodic. And it's constant, and it has a 1 at every single frequency. Now I understand why is a unit sample response really helpful, really interesting, really descriptive. When you're finding the unit sample response, you're putting in a delta sub n sequence into a system and see what comes out. I'm calling that h of n. This means we're putting in our test signal to characterize our signal is a perfect signal, a perfect test signal. It has equal amounts of every frequency there. It's like got it all in one little signal. And it's not, not some of it's a little higher than the others. There's no weighting factor. It's just flat, perfect, yeah.
In lab, when we put it on periodic noise, is it giving it an impulse?
When you put it on periodic noise, is it giving you an impulse? No. That would be, because in the lab we're using continuous time systems.
Okay.
And if I wanted to do this in continuous time, I've got to make a real live, honest to goodness impulse.
Okay.
Which means you've got to charge your flux capacitor to 1.21 gigawatts, hire a freshman to throw the switch after he vaporizes or she, see what comes out. But you got to have a really fast freshman, get somebody from the track team or somebody who plays tennis who's real fast at throwing that switch, because it's got to be instantaneous. But since I can't do that, fair enough. Okay, a couple more easy ones. Here's an unexpected one. Here's a three-number sequence, 1/2, 0, 1/2, and we can find the Fourier transform of that, discrete time Fourier transform of that, simply by plugging it into the expression summation of x of n e to the minus j 2 pi n f. I have only two non-zero values. I have 1/2 at n equals -1, right? At n equals 0, I have 0, so I'll leave that out. And at n equals 1, I have 1/2 with e to the minus j2 pi 1. I got some double negatives here, so I'll get rid of those. And I have 1/2 e to the minus, you have 1 to the plus j2 pi f plus 1/2 e to the minus j2 pi f. And somebody please tell me what that function is. Perfect cosine. Cosine 2 pi f. Be careful, that's a cosine in frequency, not time. That's the frequency domain. It looks like, well, kind of like that. Axis is off. Marker, give me a marker. Let's hope this one works. That's not a time function, that's a frequency function. Cosine, cosine, round, 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 round. Versus frequency. So I guess if I was going to plot the magnitude and phase of that, I'd have to say the magnitude of x of f versus frequency magnitude. Let's see, flips up, like that. And the phase angle, x of f versus frequency. Here it's positive and real, so I don't need any phase. Here I flipped it over, so I'm going to need 180 degrees of phase. And then I don't flip it, and then I do flip it, and I don't flip it. Minus pi. And over here I flipped it up, so I say I go plus 180 degrees phase, and so on and so on. That would be the spectrum of that. It's a real valued function again. And it's a real valued function because I had an even symmetric time function, even symmetric and real. So that's why I got a real function of frequency here. Okay. We'll do one more on Friday. We'll do the exponential case, which is pretty easy to do. And then from then on, we'll resort to tables to do this. And we'll talk about how we're going to start applying this transform. And we'll do that on Friday. Don't forget homework due. Learning objectives are posted for the exam. Please take a look at those. Questions?
How far does the exam go in the lectures?
Up through convolution.
Okay,
So
so
go
after
to-
Monday.
Right.